Consider the following completely hypothetical scenario. Let's say you witness a UFO and you collect a bunch of data on it. Let's say you collect quite a lot of data on this UFO. Of course, as it always happens in cases like this, people are going to speculate, they're going to jump to conclusions, they're going to say, oh my God, it's aliens, etc. But you're a rational person, you don't jump to conclusions so easily. So you decide you're going to test this using the scientific method and the data that you collected, of course. So you generate a bunch of alternative hypotheses as to what this could be, other than aliens, of course. And you put those hypotheses to the test. You double check everything, you analyze the data very carefully, and it turns out for every single hypothesis that you come up with is rejected by the data. They all fail. So what is the conclusion that you must draw in a case like this? All right, so this is a basic intro to philosophy of science video. I try to make it in something more, but in the end, that's kind of what it boils down to. One thing that I've been very interested in since I started this channel is the aspect of science communication, which is not about specific pieces of information, physics, biology, chemistry, etc., but a more general way in which the public engages with scientific information. What is the responsibility of scientists and science communicators in communicating about science? And maybe more importantly, or more importantly for this video, what is the responsibility of the general public when they consume, for lack of a better term, science? Often the question of science literacy or illiteracy is treated as a matter of knowing a minimum set of facts or a minimum threshold of scientific information, which is of course important, but in my opinion it is equally as important, or maybe even more important, for people to have the ability to properly engage with scientific knowledge, especially new scientific knowledge. Spoiler alert, I don't really know what the answer is. This is me kind of exploring and sort of thinking out loud, trying to find out what the best way to approach this topic is. And I think this boils down to at least having a fundamental or basic understanding of what science is in the first place. And again, spoiler alert, one more time, there's no really solid answer to that question, but if we at least think about it, we might learn a thing or two, generally speaking. It's not that long ago, but we went through a terrible global pandemic, which among many things exposed how much of a problem our scientific literacy is. You have sort of blatant misinformation and conspiracy theories, but that's not what I'm talking about today. Even among what I would describe as fairly reasonable people, which I sincerely hope is most people, I saw this confusion, the failure to understand and engage with science as it was communicated to the public. Things like, what exactly is public health, or the science of public health? How is it supposed to work? How is it supposed to make predictions through models? How are those models used, etc.? That are based on the scientific method, is not just random people making random decision pulling them out of a hat or something like that. Or often related, how the issue was often presented as the science versus the economy, not realizing that these trade-offs are very much part of the scientific methods, part of the models that they're used to make decisions. And of course, a lot has been written about this. I'll try to post some of it on the description, but what I sort of like observed and what I'm sort of been thinking about when I think back at that time is people not understanding how that information was sort of like communicated, and maybe the information probably was not communicated in the best way possible. But I think the general theme is that people didn't quite know how to engage with information as it was being communicated. By the way, people still are dying from COVID, but I guess the moment's gone, so nobody cares. Of course, this is a huge topic that I cannot possibly address in a few minutes, but one thing that kind of jumps out of this whole mess is something that, again, I've been thinking about for a while now, sort of in preparation for this video, is sort of like the relationship, or the way we understand the relationship between science and the truth, or science and reality, if you will. And how we're supposed to understand that, how we're supposed to maybe do with the information from that understanding, if that made any sense. And I hope the explanation that I'm going to give for the rest of the video will have to clarify that question a little bit. In the example that I started the video with, the one with the UFOs, the question we ask after doing all these experiments and tests, whatever those are, well, is what is the truth? Or maybe in a maybe less absolute sense, what should we take it as the truth to be, or the closest approximation to the truth, if that is the best thing that we can know? Like if you were going to place a bet in Vegas, that sort of thing. The answer is not immediately obvious, and is there even an answer in the first place? I think something like this is important to know, and because we are presented with scientific information, to put it generally, all the time, we need to know what to make of it. As with most things, people a lot smarter than I have already thought about this question quite a bit. It's the kind of thing that we have no choice but to consult the philosophy of science to even get close to an answer. So I guess I have to pause this and go and read some books, and then I'll be back shortly. So a little disclaimer, of all the branches of philosophy, I find the philosophy of science the least interesting, and it's probably the one that I read the least about. At a glance, it seems like it's trying to define a fluid and imperfect human endeavor into very strict terms, when in reality it might not be that way. All the major movements in the philosophy of science have sort of like strengths and weaknesses. And it seems to me that there's no unifying theory that you can come up with that will withstand all possible scrutiny. There also seems to be pretty much, at least in everything that I read, a heavy focus on physics in these texts, and even a certain kind of big picture physics like Newtonian and relativistic and quantum versus classical, things of that nature. It misses a big portion of scientific fields that might not work that way. Although, to be fair, I've only read a tiny portion of the texts available in philosophy of science, so I'm sure that other texts or later philosophers probably have clarified these points to make them far more satisfying and nuanced. Ultimately, I think I enjoy the continental philosophers a little bit more than the analytic philosopher, which is what the philosophy of science kind of falls into. If you're not familiar, continental philosophers are kind of the cool guys wearing trench coats and ditching school to smoke behind the bleachers or something like that. Whereas the analytic philosophers are like the nerds talking about science. But you know, someone's got to do it, and it sure as hell's not going to be the cool guys, so I guess we're stuck with that. Still, learning about all the major theories that the philosophers of science have come up with, primarily in the 20th century, was very illuminating. It helped me contextualize a lot of things that, as a practicing scientist, I either understood intuitively or had learned from experience or from conversations with other scientists, etc. And also helped me realize that a lot of things that I kind of took for granted that perhaps I thought I understood intuitively, maybe were not as solid as I thought. So that said, let me introduce some of these concepts to you. Perhaps the most influential philosopher of science is Karl Popper, who's, for some reason, when writing the script, I kept misspelling as Karl Pooper, and Google Docs never felt the need to spell check that for me. So I have to make sure I don't say that, so I don't say Pooper for the rest of the video. I think I've corrected every mistake, but we'll see. But anyway, Popper tried to give a proper definition of science and distinguish it from what he considered pseudoscience by focusing on one trait that science has over all kinds of knowledge, and that is falsifiability. Now, the term science is a bit too broad and vague and just complicates things a little bit. So by science here, I specifically mean a scientific theory or a scientific hypothesis. I might use those interchangeably, but that's kind of what I mean. And according to Popper, the main thing that makes a hypothesis or a theory scientific is that it is falsifiable. That is, for any theory or hypothesis, there must be some experiment or test that we can do to disprove that hypothesis or that theory. Whether these tests are practical or not, that doesn't really matter for now. A hypothesis can never be proven 100% because you have to test an infinity of cases, and of course if it was proven, it's kind of a catch-22. It wouldn't be falsifiable anymore, and it always has to be falsifiable. And so we can never do that, but we can provide, in principle, a single counter example that can disprove that theory. So it can never be proven, no matter how many supporting examples you can come up with, but it can be disproven by a single counterexample. For example, Popper used this to distinguish between what he considers proper science and something that he did not consider proper science, like the psychoanalysis of Freud and Adler. To quote something that he specifically wrote, but what prevents the theories from being scientific in the sense here described is, very simply, that they do not exclude any physically possible human behavior. Whatever anybody may do is, in principle, explicable in Freudian or Adlerian terms. The point is very clear. Neither Freud nor Adler excludes any particular person's acting in any particular way, whatever the outward circumstances. Whether a man sacrificed his life to rescue a drowning child, a case of sublimation, or whether he murdered the child by drowning him, a case of repression, could not possibly be predicted or excluded by Freud's theory. The theory was compatible with everything that could happen. Basically, psychoanalysis is not science, according to Popper, because psychoanalytic theory is not falsifiable. If your hypothesis is that you want to sleep with your mother, then you can probably massage that into explaining any action that you take. Let's call this position falsificationism. Right here. And I would say this is probably the main way in which scientists today think about science. Maybe not strictly in Popper's original version, but in some modified form, some evolved form, I would say that this is a fairly uncontroversial stance in modern science. A theory remains valid for as long as one of our tests or none of our tests or experiments have disproven it. If that happens, we have to come up with a new theory or modify the existing theory in some way and begin the cycle again. It does sound intuitive. A couple of important things to note, however. Popper's falsificationism was historically important because it rejected and solved many of the issues that existed with the inductionist or the logical positivist view of science at the time, which was also the relatively dominant view of science. The view maintained that observations led to theories through inductive reasoning, which then led to prediction through deductive reasoning. Popper and others, of course, pointed out that observations are rarely separate from theory, especially as science progresses and becomes more and more complicated. Theory is always part of our observation and is part of how we interpret those observations. Or even something like experiments, for example, are so very complicated. The further you go into modern times, the more complicated they become, and they are rarely independent of any kind of theory. The second point that I want to make, falsification relates very nicely to the way we do most science today, which is by hypothesis testing. Now, that's a separate thing that Popper didn't write much about. Hypothesis testing, or more specifically, is known as null hypothesis significance testing, which was developed around the same time in the early part of the 20th century by Fisher, Pearson, and then was developed further by other people after them. But it involves testing a so-called null hypothesis, usually the opposite of what you want to prove or what you want to investigate, rather, and rejecting or failing to reject that null hypothesis based on some probability threshold. I see this as sort of a statistical modification or a statistical version of falsificationism, even though there's evidence that Popper himself wasn't particularly keen on this approach. But in my opinion, I think falsificationism fits very nicely with hypothesis test, and indeed, it is the main way by a large margin of how we verify experiments today in most branches of science. So, like I said, falsification is quite a reasonable position, and I have to confess that despite all the criticism and legitimate flaws of falsificationism, there's an undeniable appeal to the theory and how simple it is. That said, there are a few problems with it. There are a few legitimate criticisms with it. The most important one is that experiments can fail for a variety of reasons, not necessarily because the hypothesis being tested is false. In fact, that's probably the more common scenario. Most obviously, science experiments are really, really hard. Experimental error is not only common, but it can also be very hard to detect or isolate it. And even without the presence of explicit errors, there are also matters of statistical significance and measurement uncertainties that can greatly complicate things. If we were to sort of like reject the theory at the first sign of failure, then hardly any theory would ever survive, like even the simplest kind of scrutiny. There are many examples in history where sort of the technology to test a theory did not exist, or did not exist in a sophisticated enough form until many years after the theory was proposed. And early astronomy before telescopes is a common example of this phenomenon. Now, this is not necessarily a problem with falsificationism per se, in an abstract and theoretical sense, because technically you could argue that it's not falsificationism's and Popper's fault that people may do experiments badly, and of course if a wrong experiment or a bad experiment or experiment that did not take into account every possible thing that it should have taken into account, if that falsifies a theory, then it's just a bad experiment. It doesn't mean that the theory should have been falsified in the first place. But it is a problem in the practical sense, because it's not that simple to know the difference, and sometimes it might even be impossible to know the difference, and sometimes the difference may be limited by whatever we can achieve technologically at this point in history. So basically, it is much more complicated than sort of the abstract theoretical sense that kind of Popper may have been thinking about when he was thinking about this topic. Another practical but notable issue is that scientific hypotheses are rarely simple. They're rarely simple logical statements. Whether it is explicitly stated or implied, a hypothesis that you may be testing can depend on so many underlying assumptions or auxiliary hypotheses that if something fails, if your experiment fails for whatever reason, it can be very difficult to detect which part of your hypothesis failed. Is it something that is main, or is it something that is an underlying assumption that maybe perhaps you were not even thinking about? Think of something as complicated as testing a new drug, which can involve so many moving parts in this process. It's, there's physics, there's chemistry, there's biology, and all the sub-disciplines within, and even something like psychology or sociology during the testing of this new drug. If something goes wrong, if something fails, it's hard to know exactly what went wrong, what part of your whole bag of assumption is that made this experiment not succeed, and can you identify that? It's rarely simple, sometimes even impossible to do that. And of course, these inherent assumptions can also be part of the experimental setup, as like we already said, no experiment is ever independent of theory. Imagine you're using an electron microscope to do some experiment and you're a biologist or a cell biologist, something like that. Think of all the physics that goes into the functionality of an electron microscope. All the physics, the engineering, all of that, all of which might be entirely unrelated to what you are trying to measure. You know how to use an electron microscope, but you don't necessarily care about all the physics that go into making an electron microscope function. But of course, whatever hypothesis you're testing, those physics are inevitable part of your underlying assumptions. If your experiment fails, it's not necessarily because your hypothesis was wrong. It is possible that there is some limitation of the electron microscope that you may not have been aware of when you started the experiment. Now, you could argue that this is unlikely, that any experienced user of an electron microscope would be very aware of its strengths and limitations, but hypothetically, I think the argument still stands. Lastly, the way falsificationism is articulated, with emphasis on falsifiability or the fallibility of science in general, can be misused in the hands of bad faith actors or people who don't really understand how science works. And I guess that's kind of the point of the video. It can give idiots online sort of a carte blanche to reject any science they don't like or don't understand, or cast doubts on any new science under the guise of falsifiability. Funny enough, this is precisely the argument or the strategy that Mac uses in the show It's Always Sunny in Philadelphia to cast doubt on evolution.
And he disproved that theory. making Aristotle and everybody else on Earth look like a bitch.
Of course, this is based on a misunderstanding of falsificationism or a bad faith presentation of falsificationism, whichever, pick your poison. But because a theory must remain falsifiable at all times doesn't make it less reliable. In fact, it is more reliable because it has withstood many tests, and especially in modern science, actually, when theories are falsified, they're rarely replaced wholesale. They're usually modified or adjusted in usually very slight ways. To quote Alan Chalmers, the sense in which science is fallible does not alter the fact that laws and theories can be confirmed to such a high degree that they cannot possibly be completely on the wrong track. Nevertheless, it does remain a flaw of falsificationism, in my opinion, because the potential for misunderstandings is there. And again, that's kind of the reason why I kind of decided to make this video, to clarify such misunderstandings. Pointing out the nuances in scientific fallibility, while it can be exploited by kind of science denialists and bad faith actors, I think it ultimately strengthens our scientific literacy.
Only problem is, they kept being wrong! Sometimes. Oh, this is insane, you fool!
All that aside, I still maintain that falsificationism remains an attractive notion, if nothing else, as sort of a Platonic ideal for what a scientific theory or a scientific hypothesis should be, or again, in sort of an ideal sense. And of course, many people after Popper have sort of written about it, talked about the flaws, proposed fixes, or more nuanced versions of the idea, but I think the crux of it remains more or less unchanged. Alright, I have to re-record this section because I recorded it once, but the microphone wasn't working. I didn't realize that, so I have to do it again. And it's too bad because I gave the performance of a century and I won't be able to replicate it. So now it's just going to be boring and dry, but what are you going to do? So after Popper, the next major influential philosopher to arise in the 20th century was Thomas Kuhn, and his view of science in terms of paradigms and paradigm shifts. Now, I've seen Kuhn and Popper presented as sort of opposing ideas, but I don't think that's the case. There's a lot of overlap between the two, and it can even be said that their aims were slightly different, with Kuhn focusing more on trying to explain and describe the history of the scientific development as he saw it at the time, rather than give a strict prescriptive view of science, which is, you could argue, what Popper tried to do. In a simplified way, you could summarize Kuhn's approach with this diagram. So the majority of this cycle is occupied by what you would call normal science, or the so-called paradigm, the normal state of affairs, if you will, that scientists tend to operate under. It always remains a sort of a central assumption in everything that scientists do. Falsifiability still remains a thing, but under normal science, scientists don't really try to falsify the paradigm. Instead, they work on smaller puzzles and problems that add to the overall knowledge of the paradigm. They solve problems within that paradigm. That doesn't mean that paradigms remain unchallenged, but overall you spend most of your time assuming kind of the usefulness of the paradigm. And all this is quite a pragmatic approach. For example, say you're trying to study the motion of the planets in the solar system using Newtonian theory. If something goes wrong, you don't really question the paradigm, i.e. that Newton's equations are wrong. Instead, you first look for errors elsewhere, because realistically, that's far more likely. And we discussed some of why that is when we talked about Popper. Under the course of normal science, of course, anomalies may arise that no matter how hard you try, you cannot explain under the current paradigm. And this, when it happens enough, leads to a crisis. The anomalies need to be significant, and they also need to be relatively numerous to lead to a crisis, to question the current paradigm. This leads to a scientific revolution and eventually to a new paradigm. And so it goes, and the cycle continues after that, the same as before. One of the examples of this happening is, of course, moving from Newtonian theory to the theory of relativity at the beginning of the 20th century.
Making him yet another stupid bitch! Are you seeing a pattern?
in my admittedly limited reading, I've kind of gathered that Kuhn has sort of become a darling among philosophers of science, and he was certainly very influential after he wrote his main book. And many people, many philosophers have sort of embraced his ideas and developed them further after him, not always in the same direction. For example, you have Lakatos, who kind of took them and sought to bring them closer to Popper, whereas on the other side you have Feyerabend, who completely embraced the relativistic aspect of Kuhn's ideas. I must confess that I do not find Kuhn entirely that convincing. In fact, you could even argue that this whole video is a thinly veiled excuse to shit on Kuhn, but not really. Still, there are a few things that kind of bother me about his approach in general. First, it's too physics-based, and only certain kind of physics, in fact. And of course, you could argue this about a lot of philosophers of science, but certainly Kuhn is no exception in that regard. Like a lot of the ideas that he talks about, they would be hard to, and there are usually sometimes examples given that are not physics, but I think overall, in a big picture sense, it's hard to take some of his ideas and then adapt them into other sciences, especially in a modern context. The other thing is, I don't know that we get an entirely satisfactory definition of what exactly a paradigm is. I'm on board the idea that the definition has to be somewhat flexible. It cannot be too strict, but even that said, I still found the way it was presented a little bit too vague. There are many levels of, I guess you'd call them generality, that you can zoom in within any given field, and each of those points could be part of the paradigm, and it's unclear how would you define it. For example, you have quantum mechanics, and then you can sort of zoom into quantum field theory, the standard model, or something else. What exactly is the paradigm there? And the thing gets even more complicated if you go outside physics. For example, is evolution a paradigm? Well, evolution today has evolved, no pun intended, tremendously, and would be almost unrecognizable to Darwin. So how exactly would you define a paradigm there? And the other major point that I wanted to make in regard to Kuhn is that, of course, he bases his idea on the history of science, but I've talked about this before, but examining the history, any history, but especially the history of science, can be a little tricky, because when you examine history, you tend to focus too much on the big picture, the leaps, and then the sort of like the tiny little details are often lost or ignored, and sort of like the gradual process of history becomes more coarse, and you sort of see the leaps as bigger than what they may have been. Now, again, I'm not saying that there aren't leaps, but they're often smaller than we think. And of course, as we move further into the history of science, as we get closer to modern times, the process becomes more and more gradual, and it doesn't always match this kind of like stepwise progression of normal science to crisis to revolution and rinse and repeat that Kuhn presents. And speaking of history, and I've noticed sort of like this prevalent viewpoint when reading about this topic, is something that came up often, I guess, is the idea that any philosophy of science must first and foremost accurately describe the history of science. And to me, that seems a little bit of a silly requirement. I think it's kind of absurd to have one single philosophy of science describe both or all the science that Aristotle did, and the science that Newton did, and the science that Einstein did, and whatever it was that I was doing a few years ago in grad school. I think that's a non-starter. Science is not monolithic. The practice of science has changed throughout the decades and the centuries as much as the content of science itself has changed. I'm sure there's more nuance to this, and I've probably only scratched the surface of Kuhn's ideas and the people that followed him. Still, there were a couple of ideas or a couple of things that I really appreciated while reading Thomas Kuhn, and I think they're very useful to kind of the point that I'm trying to get across through in this video. I doubt Kuhn was the first or only person to point this out, but one thing that I really appreciated is that he did emphasize the notion that there is some subjectivity within science. There are economic, cultural, psychological, sociological factors that always influence the decisions of scientists, independent of any objective truth, which is often, what the purpose of science is. Funding may influence what you choose to study, or when you encounter the so-called anomalies, as he calls them, under a current paradigm. There's obviously some subjectivity to how you respond to that and how you interpret it. That is not to say that science itself is subjective or that scientists act entirely subjective ways. Of course, some have argued that, but that's not what I would argue here. It's just that no matter what you do, you can never remove the human element, flawed as it is, from the scientific process. And so like the second point, despite my complaints about the vagueness of the paradigm, I think it's still a very useful and practical concept. And I think it reflects quite a bit how scientists think about science in a larger sense. While it may be a little challenging to define a paradigm, that one exists is a fairly natural and reasonable assumption. I think it would be too impractical to question everything. That's kind of obvious, right? Instead, scientists spend time solving problems within a baseline of assumptions, and only when those problems become harder and harder to solve, that's when they step back and look at those assumptions that they began with in the first place. To anticipate bad faith actors, again, it is easy to see how this can be misused to make arguments that scientists are too stuck in their paradigms and won't explore new ideas, or that they've stagnated, etc., etc. And of course, I'm sure you have seen those arguments. I don't name names in the channel, but everybody has heard such statements, and fortunately, that's not really how any of this works. It makes no sense to reject a paradigm when it works, and when it doesn't, people actively work towards the solution. That has worked pretty well so far, so it doesn't make sense to change it. Moreover, science itself has changed quite a bit, like I already mentioned when I was talking about the history of science. And if we think of this in terms of probabilities, the current paradigms are the most verified of any in the history of science, and the likelihood that they will be toppled are much smaller than they have previously been throughout the history of science. And the degree that which they will change, if they ever do, is going to be inevitably smaller. Like it's unlikely that quantum mechanics or evolution will be shown to be completely wrong. I mean, it would be completely impractical to even think in those terms, and nothing would really get done, right? I think when those theories do face problems, when they do, if they do, the corrections are probably going to be minor modifications rather than, wholesale replacement. Okay, so where does that all leave us? I hope the theories that I've talked about in this video give a decent idea of how to think about scientific theories and hypotheses, both new and old. But let me introduce you to a visualization that I think might help with this process and thinking about this process. I drew it here, but I think I'm just going to show a picture because I just want to make sure that it is clear what exactly I mean. So, okay, let's assume that this two-dimensional graph contains all valid scientific theories. That's a little bit vague, but I think it's clear enough for the purposes of what I'm trying to do here. So the x-axis represents the time or maturity of a theory. The further it is to the right, the more evidence there is in support of that theory. And so the more likely it is that it makes for an accurate representation of objective reality. This is where Kuhn's paradigm lives, all the way to the right. For instance, over here to the right, you might find something like quantum mechanics, a very mature theory, and to the left, you might find something brand new, like a new particle or a new cancer drug, things of that nature. Falsifiability still remains a requirement, always. Any theory, regardless of where it is on this axis, still remains falsifiable and can never be said to be proven in the strictest sense of the word. But the further to the right you are, the stronger and more numerous the evidence needs to be to falsify it. You can think of theories as moving dynamically along the axis. As evidence increases in support of a theory, it moves to the right, and if evidence emerges against a theory, then it has to move to the left. For a theory all the way to the right, it has a long ways to go before we have no choice but to abandon it. The y-axis represents complexity. It's somewhat of a vague and, of course, a relative term, but I don't think you can have it any other way. As I mentioned earlier, think of this as how many components or moving parts a theory or a hypothesis has. For example, something like quantum mechanics would be relatively low on this axis, while something like drug development or public health would be relatively high. A theory or a hypothesis in those areas are more complex, are made of many moving parts and many underlying assumptions. In this case, the more complex the theory is, purely from a numerical argument, the more likely is that one of its arguments would could fail, or if it does fail, the harder it is to know which one it is that fails. This relationship is not as clear as it is in the case of the x-axis, but think of something like fundamental neuroscience versus psychology, which is largely an emergent property of neuroscience, you could argue. Relative to each other, neuroscience is much lower on this axis than psychology, and in a very loose sense, it's simpler to verify or reject a hypothesis in that field. On the other hand, a hypothesis in psychology is much more complex and harder to test, and it's much harder to verify or reject, and when you do, it's much harder to know which component exactly failed. Another interesting example is biology versus public health. Public health would considerably get higher on the y-axis because it's so much more complicated. That said, many theories of public health have been studied for decades and are relatively mature, so it would also shift fairly to the right in the x-axis. So there you go, I used both axes for once. Still, such theories would be highly trusted, but it's probably fair to say that they're more falsifiable than something of equivalent maturity in biology. So I hope that makes sense. I think this is a good way to think of science, at least as an initial approach. I'm not saying it's foolproof, not even close. I'm sure you can poke a million holes in this idea, but I think it's a good way, especially for lay people, to sort of, when reading and engaging about science, to think of science sort of in those terms. For example, if you're reading about some crackpot trying to prove that the Earth is flat, I think this is a good way to think about it. Of course, you're welcome to learn the science and convince yourself why Earth can be flat in scientific terms, but this is a simple example. In many cases, that can be an unrealistic goal for everyone to be able to do, simply because not everybody has that kind of time to devote to learn complicated things. So I think you can think of it instead, to go back to this example, as where the shape of the Earth would fall in this graph. It's probably way to the bottom right, which means that the evidence to disprove it must be extraordinary and unlikely that some YouTuber stumbled on it. To quote an old dead president, it's a long twilight struggle and must all bear the burden for it. Again, this is somewhat of a pathological example for sure, but I hope it illustrates how thinking about science in these terms can help when consuming and engaging science. Okay, so I have to talk about the example that I started the video with. A bit clickbaity, if I must say so myself. I'm not entirely sure what the correct answer is for that one. For one thing, it's an extremely contrived and improbable example. It's quite unlikely that the evidence would be so overwhelming that it could unquestionably reject every possible alternative hypothesis that we could come up with. Still, utilizing the graph here, the idea of aliens is so unlikely that any alternative hypothesis would be pretty far to the right of this graph, and the evidence would have to be extraordinary to suggest otherwise, that is, to suggest that it is indeed aliens. In a hypothetical example, it's hard to say how much evidence is enough evidence, so sorry, I don't really have an answer for that. There is, however, a real-world analog to the hypothetical example that I came up with, and that is the wow signal from the 1970s. The wow signal was a strong, narrowband signal detected in 1977 by the Ohio State's Big Ear radio telescope as part of the SETI project at the time. This was before the official SETI. And the signal was quite strong and stands out quite noticeably from the background noise that the person who discovered it while analyzing data on paper wrote "wow!" on that piece of paper, and that's really where the name of the event comes, the wow signal. Of course, because of the characteristics of the signal and because this was a SETI project, one of the hypotheses is that this could have been artificially generated by an alien intelligence. However unlikely that is, no alternative hypothesis has been confirmed and the signal has not been detected again. So it remains an open question. Of course, the difference between this, the real world signal, and the hypothetical example I came up with is that there's really not enough data in the real case to test any hypothesis in a satisfactory manner. It will probably remain unsolved forever. Could it be aliens? Maybe, but based on everything we've talked about today, I think the right course of action is to assume that it isn't, since that is the far more likely scenario. That might be a little disappointing, but hey, it is really the best that we can do.